Not late, relax. Hold on. Don't drop nothing, don't break it. All right, first I owe y'all an apology. But I was supposed to be sending notes and recordings, and yesterday I had I was submitting a grant and didn't have time to do that, but I'll send everything today. You'll get a big giant announcement at some point. But by now, everybody should have the handout. We're in module 2A, which is dealing with nucleophiles and electrophiles. This is a very dense section. So we'll probably, the next test will probably be only this. If we take it on schedule, it'll just be this and nothing else. So we left off on, when we left off talking about nucleophiles and electrophiles, and then we finished up talking about types of reactions, right? Substitution, elimination, addition, and rearrangement. So let's say that way. It's coming up at some point. Only thing about this hybrid business is you got tech issues, you got a problem. Start again. Doesn't help that Zoom is a terrible program at times. One second. Sorry. All right, so when we left off, we were talking about these different types of reactions, and we'll sum them up in a second, but I do want to cover the bottom reaction as well as, so we've done elimination, substitution, and addition. What we haven't done is rearrangement. And rearrangement is a special type of reaction, all right? And so we'll talk about that with these two examples at the bottom. And then, so let's look at this example right here. What does it look like happening here? This is a good example. And the reason I like this example is because it makes you think. What happened? Chlorine got replaced by hydrogen. Good. How did that happen? What is it? So what would you say under normal circumstances happen when we replace one atom with another? Okay, but also we substituted, right? So that it looks like a substitution, but anytime you have an sp2 carbon, which is right here, that carbon in that double bond is sp2. so it's this. Right? You can't not substitute on an sp2 carbon. Right? Cannot substitute. So this is an addition followed by elimination. Right? You can't substitute on an sp2 carbon. I'm gonna write that down. Right, so in that case, what you could do is add some hydrogen source and then eliminate to kick off chlorine. And I don't want to get into the mechanisms just yet because we're going to look at some examples down below. All right, so the other type of reactions that we got, now we have substitution, elimination, addition, and then the other type of reaction I'm going to cover is what we call a rearrangement. Right? Look at that example and tell me what happened.
Hydrogen to where the plus charge was?
Yes, so the hydrogen that's here moved here.
Yes.
Go ahead, I heard, and
Plus
then,
charge moves to where the CH3 is.
yes, good. So what happened in this case, and I'm going to show the arrows here, is the hydrogen that was here ends up here. Right? So a rearrangement is the movement of atoms and electrons within the same molecule. Right? It happens within the same molecule. So I'm going to give you a term for that. It is intra-molecular. Intramolecular movement of atoms and electrons. Intramolecular, that means it all takes place inside the same molecule. There are no external forces acting on this molecule. Can you see that, Cameron? Good. All right, so this moved here. This type of rearrangement, I'm gonna go ahead and give you that too. It's called a hydride shift. The reason I'm giving this to you in so much detail is because you're gonna see it again. It's called a hydride shift. And I'll explain what a hydride is too. Right, so if I move, let me ask this question. If I move hydrogen only without the electrons, what am I moving? Am I moving H plus or H minus? If I just take the hydrogen and move it, just H plus to a plus charge, that's not going to work. I need electrons. So I have to take the hydrogen and the electrons in the bond and move all of it, right? So the way that the arrow that I would use, I would start here at the CH bond. And I would just draw a curved arrow where that plus charge is. Uh-oh. Notice where my arrow starts, between the carbon-hydrogen bond, in the middle of it. So the hydrogen and the electrons are moving. That's why it's called a hydride shift. A hydride is H minus. So I'm moving hydrogen and the electrons at the same time. And that's the type of rearrangement. Question, any questions about anything? Can everybody online hear me okay?
Yes, we can hear you.
I heard a whisper. I think that was a yes.
Yes.
Let's do the next example. What happened here? Same thing. But what did I move this time? I moved the CH3 group, right? This is an example of, it's a rearrangement, but it's an example of what we call a methyl shift. Right, so I'm taking this carbon, I'm just gonna move it. Here, where the plus charge. Thank you. Methyl shifts, hydride shifts, both follow the same mechanism. The atom and the electrons move to wherever the charge is. All right, any questions? So we got four types of reactions that we looked at. And those four types are what? Elimination is one,
Addition,
okay?
subtraction,
Subtraction or multiplication or substitution.
oh, so,
Substitution, good. You know what? Normally when I teach this, I'll throw that in there just to see who catches it. Subtract, I'll say subtraction, division, nobody else. Everyone's like, yeah, it's subtraction. It's not, it's substitution and rearrangement. Those are the four general types of reaction. And they happen in different ways. They all have different mechanisms, right? All have different ways of getting from point A to point B. All right, let's look at another set of reactions down here where we have the arrows. So we're going to draw the products and we're going to determine what type of reaction it is. Is that all right? So let's start here. What are we doing? We're starting with this one right here. What do the arrows indicate? Yeah, good. Where are these electrons going right here? Right here. What does that normally tell you? That's making what? Making a pop on. That's good. So here, this pair of electrons moving here means I'm making a pi bond between carbon and oxygen. What does this arrow tell us? I'm breaking a sigma bond and giving the electrons to oxygen. Is that right? So over here, let's just draw what we're going to get. Over here, I'm going to have this. Is that right? Because this arrow here says what? That I am moving that pair of electrons to make a pi bond. Is that right? And then right here, I'm going to also have this. This is going to be plus O. Okay, 2, 3. Yes or no? All right. And oxygen is negative because it picked that pair of electrons up. All right, what type of reaction is that? I lost something and I made a pi bond in the process. It's an elimination. Good. All right, I lost a leaving group and I made a pi bond in the product at the same time. What about the bond making and bond breaking? Is it hetero or homo? And how do you know? How can you tell? If it was homo, the arrows would be fissures, single headed. So everything here is either heterogenic or heterolytic. All right. So when I'm making that pi bond, that's going to be heterogenic. Yes. when I'm breaking this sigma bond, this is hetero. Anytime you use double-headed arrows like that, everything is hetero. The bond breaking is heterolytic, the bond making is heterogenic. All right, questions? Any questions about anything so far? All right. Let's do.
What is the
Let
lead?
me turn my volume up on my laptop because I can hear you, but I can't hear you. Go ahead.
I want to know which one was is it leaving group? Leaving?
Yep. Oh, good question. So this, you see how the arrow is pointing to the oxygen and looking like it's forcing it out?
Yes.
That's my leaving group.
Okay.
Great question. I'm going to abbreviate this as LG, if that's okay. Every elimination has a leaving group. Every substitution has a leaving group. Great question. All right, let's do this one up here. Let's draw products of that. This is a special case, but we can still discuss it. What do you think? What's happening there? What do these two arrows indicate right here? In this case, it's, okay, so addition only happens on pop-up. So if you have a double bond and you react something with it, that's addition. That's a way to tell when addition is happening. Because your star material is always going to be a pop-up, something with a pop-up. But what's happening between H and Br? What do those two arrows meeting together like that mean? I'm making a bond between them. The bromine is donating one electron, and then one electron is coming from that CH bond. Is that right? So on the product side, it's going to be HBr. That's one of my products. Plus what? What does the arrow here mean? Going back to carbon. Okay, let's think about it. The CH bond is a sigma bond with two electrons in it, right? If one of the electrons leaves with the hydrogen and ends up bonded to bromine, you have one electron coming back to carbon. What's that called? Anybody? A single electron, a single unpaired electron. There's a special name for that.
Radical.
Oh, thank you. It's called a radical. Right? So this particular reaction doesn't fall into one of our categories immediately. It is a precursor to one of our types of reactions. This process right here, I want you to get familiar with it because you're going to see it again. This process of removing H and removing one electron is called abstraction. Radical abstraction. You're going to see this in the next section when we do radical reactions and go through the mechanism. That's why I put it here. All right. What this is, though, is a precursor to another reaction. So that radical, if I pair it up with a bromine radical, here are the two arrows coming together. That means I'm making a bond between those two. I'm sharing electrons between them. If I pair that up, that's what I get. Is that right? Now, what type of reaction is that overall? Substitution. I took off a hydrogen and I eventually added a bromine. Are you following? So the whole process is an example of what we call a substitution, but it's a radical substitution. Right, radical substitution is another way to get to substitution products, because you can do it in a radical fashion or a polar fashion. All right, any questions so far? We good?
Are we gonna, the-
Oh, good, that's a good question. We want to, I'm trying to get
I
the
was
survey.
asking.
I'm trying to get the survey. I got it. What is, okay, so when I break that CH bond, Chase, I'm gonna give you first deals on it. Is that homo or hetero, and is it lytic or genic if I'm breaking a bond?
If you're breaking the bond,
Uh-huh,
it's gonna be homo-
homolytic. So the CH bond cleavage is homolytic. And then I made the bond between bromine and hydrogen. So that's gonna be, sure. Is that right? Homo, because each atom is bringing one electron to make that bond. So homolytic means I'm breaking a bond and each atom is taking one electron. Homogenic, I'm making a bond, each atom brings one electron. All right. I'm going to, because I can't remember, I know I didn't send the videos out with the different bond making and bond breaking, but I'll send all of it today. Just the matter is we reinforce. Normally I like to send it out ahead of time, so we prep, come in and be ready to discuss, but that ain't time. All right, let's do this one right here. What is that? Actually, if somebody want to come up and draw the product? Let's take a minute. Take a minute. If you're online, take a minute and draw the product of this reaction. All right, anybody got it? Yeah.
I have some.
We'll wait to find out. It's better to be wrong on this side of the exam than be wrong on the exam. So it's okay. There's no penalty. Okay, I'm going anywhere. I'm going anywhere. What is this? What is the arrow going from the OH to carbon mean? What does that mean? Invite answer. What does that mean? This arrow right here, making a bone. So over here, these electrons are being donated here. So that carbon, that oxygen are gonna be bonded in the product.
Like that.
Yeah, like this, a sigma bond,
Yeah.
but not here. It's the oxygen, right?
Okay.
With 2 lone pairs left, but it gave 1 up. Is that right?
Yeah.
Okay, great. Plus what?
Plus-
What is iodine doing? It's leaving and it's doing what? Taking a pair of electrons, is that right?
Yeah.
Okay, do you have a charge on iodine?
I didn't draw it, but yeah.
Okay. Are we following that? So anytime you have an arrow between 2 atoms, like from coming from one atom to another atom, that means it's sharing electrons to make a sigma bond. All right. What type of reaction is that?
Is this substitution?
Substitution. What's my leaving group?
Iodine.
Iodine is my leaving group. Good. All right, so iodine is my leaving group. Oxygen, in this case, ooh, this is good. What is oxygen?
Is it a nucleophile?
Say
Is
that
it a
again.
nucleophile?
It's your nucleophile. Good. Oxygen is my nucleophile. What does that make the cyclohexyl iodide right here? The ring. What does that make the ring? If oxygen is the nucleophile, makes the ring the electrophile. And where is the electrophilic site in the ring? Since we know that's the electrophile.
The carbon that's bonded to the iodine.
Carbon where your leaving group is. That's where the reaction takes place, right? That's where the oxygen attacks. And so this carbon right here, the electrophilic site. Right, in the electrophile, wherever the reaction takes place, that's the electrophilic site. All right, good. Last question is here. All right. What do we have? Let's just go through the arrows. What does this arrow mean right here? Making a bond out. That's right. What does this arrow mean right here?
The double bond to
Yes, and breaking the carbon hydrogen bond at the same time, right?
Yes.
Good. What about here?
Bromine is gonna have 2 additional.
Excellent. 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 Over here, my product should look like this. Is that right? Yes or no? Yeah. You mean to make H2O and all that? Yeah, yeah. Good catch. All right, so that means that plus H, I'm gonna write it as HOH. Plus what? What's that? What type of reaction is that? I made a pop on in the product. What type of reaction always results in the formation of a pop in the product? Elimination. This is a special type too, but we're going to study this later, but there are 2 types of elimination that we're going to study. This is one of the types. It's called an E2, but don't worry about that part yet. All right, any questions about anything so far? All right. Let's go. Go ahead.
So when I draw my skeletal structure,
Mhm.
do I have to have that gap?
No.
between? Okay.
You mean
So I was like, can I just draw the whole thing and then hook on the
on top?
Yeah,
Yes.
okay,
Or underneath?
yes.
It's all semantics.
Okay.
Yeah, that doesn't change anything, but yeah, you can do that. All right. So here, we're gonna kind of push this to the next level. It asks us to put the arrows in, identify the nucleophile, electrophile, the type of reaction, and it also asks us to calculate the delta H for reaction. So I'm gonna take a minute and talk about that, calculate the delta H. All right, this what page here. So we gotta pause right here, talk a little bit about the thermodynamics and kinetics of reactions. So here we're gonna get all this information, delta H, delta G. We're gonna learn about what a transition state is. We're gonna learn about intermediates. We're gonna learn about how to calculate delta H, all of that. Let me put that up here as a precursor. Right? All these things are gonna help us with that delta H calculation, that part. So for any reaction, let's say we have something like this. We have something like that. What happened overall in this reaction? What type of reaction is it? I took the iodine and I replaced it with OH. It's a substitution, right? And doing that substitution, let me put the arrows in. Let's do that. This carbon. Right, in doing that substitution, what bonds did I make and what bonds did I break?
Broke a signal
Okay,
between the CH3 and the I,
okay,
and then you add the electron, the CH. the CH3.
mm-hmm. So, yeah, so in this reaction, I broke, which is I broke carbon iodine bond. Is that right? Then I made carbon oxygen bond. Everybody okay with that? I broke the carbon iodine bond, made a carbon oxygen bond. right? So for this particular reaction, every reaction has what we call a reaction profile, right? And that is going from star materials to products over a period of time. So if I were to draw the profile for this reaction, I'm just going to draw it in general. So this is energy. This is time. Sometimes in the book, you might see it say the reaction coordinate. Right. I'm not going to show whether it's endo or exothermic yet, because we don't know that yet. So what I'm going to show is on here, these are my reactants. They have to cross a certain threshold to get to the products. We can determine endo and exothermic based on the energy of the reactants or the delta H. That's going to help us with that. All right. At the top of the curve, this is what we call our transition state. What do you think that means? Keep in mind, I'm starting at my reactants. Over time, I'm moving to my products. What do you think the term transition state means? Or the phrase?
The point in which it actually seeing.
So things are changing, right? Bonds are being broken and bonds are being formed. That's what that is, literally. So this is bonds breaking and bonds forming. Every reaction goes through a transition state. Depending on the type of reaction, what I mean by that is if it's exo or endothermic, either bond making is very extensive and bond breaking is basically complete, or bond breaking is incomplete and bond making is also incomplete. So we'll talk about that, right? So every reaction follows this. So we can actually figure out for this reaction all of these parameters. That's one other thing I want to talk about, and that's this. That's the distance between the reactants and the transition state. We call that what? Anybody know that from CHEM? It's called the activation energy. Activation energy controls the rate. If it's high, the reaction is going to be slow. If it's low, the reaction is going to be fast. It's that simple. So this controls the rate of the reaction. All right, so for this reaction, let me show you the transition state. I want to show you that, and I also want to show you how we can figure out if it's exothermic or endothermic and figure out what KEQ means. All right. So for the reaction that we see up top, this is what the transition state would look like. So we know that it's the carbon, that's the electrophilic site. We know that there is a there's a bond forming between carbon and oxygen. We also know that there's a bond breaking between carbon and iodine. This is a forming bond. And normally for transition state, we'll put it in brackets. We'll put a double dagger on the outside of the bracket, like a little telephone pole. And that is what it looks like. Got partially broken bonds, got partially formed bonds. Right, and it's, the reason I say I'm stressing about the bonds being broken and the bonds being formed is because that is how you calculate delta H. Unless you're doing it and experimentally in a lab, delta H is going to be the bond broken. That's the bond formed. And let me say this. Let me not just say that. Sometimes you break more than one bond. Sometimes you make it more than one bond. So it's the sum of the bond broken minus the sum of bonds. If you break two bonds, then you add those values together. If you break it 3 bonds, you add them together, right? But delta H is going to tell me whether or not the reaction is ex or endothermic, and then I can use that information to extrapolate everything else. If delta H is negative, that means your reaction is exothermic. So exothermic. In your book, it might say exergonic, but it's the same thing. If delta H is positive, that means that the reaction is endo. Do y'all remember those terms from CHEM part 2? One of them releases energy, one of them absorbs energy. All right. So based on that, we're going to be able to determine delta H, KEQ, delta G, and the activation energy. Not numerically though. So we're gonna do it qualitative and not quantitative. But in order to figure out this, we need some numbers, right? So I'm gonna in that second module, there's a chart. So we have a chart of bond strengths, and it's not there. All right, that's okay. I'll make sure we have that Friday. So once we have the chart, we can go back and calculate delta H and all that stuff. All right. Everybody's packing. So that means they're gonna ghost me. I'm joking. All right, we are gonna stop here though. And we'll pick this up on Friday. Be on the lookout for an announcement with a bunch of stuff in it today, before I go to my other office. All right, any questions?